Okay. So last time, we talked about the linear transformation and how matrices are how matrices can be related to linear transformations. So to do that, first you have to choose so suppose that I have a linear transformation, F from vector space V to vector space W. And once you have chosen the basis for each of these two spaces, then the linear transformation of these basis vectors under the linear transformation F can be written in terms of basis from W1 to Wm. And then in that case, the matrix representation of this linear transformation with respect to the basis B1 and B2 can be written like this. So which is the n by n matrix. So this the row number is the dimension of the codomain, and then column number is the dimension of the domain. And for simplicity, well, this is that this notation is not standard. So I just made up this notation. But I really just want to made up this notation just in order to clarify the basis, which basis system you're working on. And here, this basis on the top means sometime from time to time, I just want to call this guy a input basis, and this basis as the output basis. Yeah. Okay, again, all these notations and terminologies, they are not standard. Sorry about this. But and also, once you have two linear transformations, and this red and this guy has the basis B1, and this space has basis B2, and this space W has basis B3, and this composition of two linear transformation is again another linear transformation, and the matrix representation of this composed matrix, the composed linear transformation, can be written as the product of these two matrices. So this is what we have done in my previous lecture. Okay. All right. Now, today we'll be discussing some very important examples of the linear transformations, especially in two-dimensional Euclidean spaces. So in our textbook, the Professor Strang introduces three important linear transformations on plane. The first one is the rotation. The second one is the projection. And the last one is the reflection. So we will talk about each of these linear transformations. And specifically, so I will try to discuss how to find a matrix representation of these linear transformation in terms of standard basis system. Okay. All right. So what is the standard basis? You know what I mean by standard basis. So if you have a plane, then this vector to the left, to the left and length 1. This one is called the standard unit vector E1, and this guy to the up and length 1. This one I will call the standard basis vector E2. And collection of E1 and E2, I'm going to name it a standard basis of the plane. Well, I will begin from the rotations. Here, by the way, the reason that I try to make a matrix representation in terms of the standard basis, that is mainly not because the standard basis is mathematically more important or more important than the other basis. Every choice of basis, they are equally important. But however, for psychological reason, so we feel very comfortable. I believe working on the standard basis is the most convenient for most of us. So this is the reason that why I'm trying to write everything in terms of standard basis. Okay, rotation first. You know what I mean by rotation. I have two-dimensional plane and I have one vector. And suppose that I rotated this vector counterclockwise direction by theta radians. I will say Q theta. This is a linear transformation from plane to plane. This is rotation about the origin by angle theta. Well, you know, everything in radian. And counterclockwise direction. Okay, so if this vector is V, then the resulting vector must be Q theta of V. Okay, and because of our discussion in my previous lecture, we all agreed that this function is indeed a linear transformation. All right, now I want to find a matrix representation of this transformation in terms of the standard basis. So standard basis, as I told you, I mean by this one and that one. The collection of these two vectors, I will call a standard basis. Now, I want to find a matrix representation of this guy. In order to do that, I want to find Q theta of E1 and Q theta of E2. The linear transformation of each of these basis vectors, and if I can write down these two base vectors in terms of standard basis, then I can write down a matrix representation of this guy in terms of standard basis. That was the trick, right? How can I do that? Well, idea is very easy, and computation is also not complicated. This is my E1. The idea is very simple. So if you can compute the linear transformation of these two basis vectors, then you know linear transformation of all the other vectors. So this is my E1 and E2, and I am rotating everything by theta radians. So I guess this is Q theta of E1. And this one is Q theta of E2. Okay. Okay. Now, let me try to write down, I will write down this guy as a linear combination of these two vectors. This is not that hard because this is the x coordinate of this point, this endpoint is cosine theta, and y coordinate of this point is sine theta. Okay, so cosine theta and sine theta. And what about this point? What is the x coordinate of this endpoint? Must be minus sine theta. Okay. This is very easy trigonometry. You should be able to do this by now. Sine and y coordinate is cosine. Okay. Okay, agreed. So the answer is, now I want to write down this guy as a linear combination of these two vectors. So has to be cosine E1 plus sine E2. And this is minus sine E1 plus cosine of E2. Agreed? Okay. So my matrix representation of this linear transformation in terms of the standard basis the input basis is standard and output basis is another, so again standard. And this is a, well, cosine, since here I have cosine here and sine there. So the first column must have the cosine on the top and sine bottom. And I have minus sine and cosine. Thus, therefore, the second column has to be minus sine on the top and cosine in the bottom. Okay. So, so this is a matrix representation of the rotation about the data radius in terms of the standard basis. Okay. So now we know the matrix of the rotation. Oh, sorry. Matrix of rotation. Therefore, in principle, you can compute rotation of any vector very easily just by taking the multiplication of a column vector by this matrix. Well, I'm going to give you the example of this. Suppose that you have a vector a comma b. You know what I mean. So yeah, you suppose that you want to rotate a vector a comma b by the data radius counterclockwise. Then what is the resulting vector? Then if you want to compute this, then all you have to do is just nothing but multiply the column vector AB to the right of this matrix. Then this is what? A cosine minus B sine and A sine plus B cosine. This is the resulting vector. And then you can translate this result as, if you rotate this vector by theta radians, then the resulting vector, the endpoint of the resulting vector would be A cosine minus B sine, comma, A sine plus B cosine. So everything is so obvious. So everything just reduces to the matter of multiplication. Okay. Okay. Maybe this this remark is so obvious to most of you, but this is again very important. What if you compose two rotations? The first rotation is rotation by the theta, and the another rotation is rotation by psi. If you compose these two rotations, then obviously the answer is q psi plus theta, right? You rotate by theta and rotate by psi, then it's, well, practically you're rotating by psi plus theta. Well, but if you do not, so if you really want to prove the statement, then maybe you can try like this. Q well, the matrix representation of this composed linear transformation can be decomposed as a product of these two matrices, STD, STD, and times Q theta, STD, STD. Then now everything is psi. Then turns out this is the product of these two matrices. Then by using some trigonometric identities, it turns out this is cosine. This is just an easy computation. So if you haven't done this exercise by yourself, then I believe this is the right time to do this. sign, and just convince yourself that this is the real resulting matrix. So, and the final matrix is clearly a matrix that represents this rotation. Okay, so claim has been proved. Okay, all right. So this is about the rotation. Now, let me turn to the projection. Onto data line. So typically, a projection on the plane goes like this. Suppose that, well, you have the plane. Plane is the ambient vector space. And suppose that you have a one-dimensional subspace spanned by some line. So this is our name, this guy, my data line. Data line because the angle measured from the positive x-axis to this guy is theta. Well, and this is a vector space. This is a one-dimensional subspace of R2. Now, the projection is if you have some, just choose any random vector in R2, and suppose that you projected this guy, this vector, onto the data line. Then, by drawing a foot, which is a 90 degrees angle, then, yes, this, yeah. And this green vector must be the projection of this guy onto this space. Now, I'm going to name this linear transformation as P theta. So this is a linear transformation from R2 to R2. So this is a projection onto the data line. And clearly this is a linear transformation. Also, I want to find a matrix representation of P theta in terms of the standard basis. Okay. How do you do this? So this is P theta and V. So to find the matrix representation of this guy, I will need to keep track of the projection of each of the basis vectors and write the answer in terms of the standard basis. This is the theta, and this is E1. This is E2. Now, what happens if I project this guy onto the data line? Then this is the resulting vector. Okay, so this is the resulting vector. P theta of E1. So, can you figure out the coordinate of this endpoint? Well, clearly this vector is some scalar multiplication of cosine theta, sine theta, right? And now, what really matters is the magnitude of this vector. So what is the length of this vector? Wait, we know the length of this guy is 1, okay? Therefore, length of this vector must be cosine of theta. Okay. So this is actually cosine theta times cosine theta and sine theta. Okay. Okay. All right. Now, this vector, this is p theta of E2. In order to find out the coordinate of this endpoint, this is some scalar multiplication of cosine theta and sine theta. But in this time around, length of this vector must be sine theta. Okay. So this is sine theta times cosine and sine. Okay. So p theta of E1 is maybe I should write down, so cosine square times E1 and cosine times sine times E2. Okay. Yeah. So I am writing down this guy as a linear combination of E1 and E2. And for p theta of E2, this is sine times cosine times E1 plus sine squared times E2. Right? So p theta of the matrix representation of this linear transformation in terms of the standard basis is I have cosine square and cosine times sine there. Therefore, the first column has to be cosine and cosine square and cosine times sine. And since I have sine times cosine here and sine square there, so sine times cosine and sine squared. This is the matrix representation of this matrix representation of the projection. Okay. Okay, great. So if you have a textbook, then Professor Strength, he tries, well, he simply says that this is a projection. This is a projection, but technically speaking, so that is not right. So this is not a projection. This is merely a representation of the projection in terms of the standard basis. Okay. All right. Hold on. So also, I found very important observation. So, so the first column means this vector, and the second column means that vector. And as you can see from this picture, those two vectors, they are actually linearly dependent. This guy is merely, so nothing but some scalar multiplication of the other. So there is only one linearly independent rank, linearly independent columns. Therefore, this matrix is a rank 1 matrix. Okay, and so in my previous lecture, so every rank 1 matrix can be decomposed into a column vector times row vector. So I must be able to have such a decomposition, which is so cosine and sine and cosine and sine. Yeah, right. So this is a rank 1 matrix. So rank 1 matrix is, well, by its nature, which is not a full rank matrix. Therefore, it doesn't have any inverse. So because of that reason, the projection is not invertible linear transformation. So first observation is the projection is not invertible. So in other words, you cannot find a inverse function of the p theta, which is very obvious. Clearly, p theta is not one-to-one function. Right? And well, as a matter of fact, this is a defining characteristic properties of any projection matrix. So if you compose same projections twice, then effectively means nothing but applying just one projection. Right? This is again very easy. So just to say that if you have a vector and you took a projection of this vector onto the data line, which is this. But if you take just one more projection for this vector, already projected vector, then that means the second projection does nothing. So therefore, taking two projection is the same as taking just one projection. Yeah.
Can we refer the metric form of linear transformation as the function?
Oh yeah, sure. Yeah, here, in this chapter, so every matrix should be understood as a function. Yeah. Okay. So if you're not trusting me, then maybe just try to multiply these two matrices. So take a square of this matrix. If you raise the second power of this matrix, I mean, if you multiply this matrix twice, then you're gonna get exactly the same thing. Okay, so all right, and the last, number 3, is two-dimensional reflection about the data lines. So what is a reflection? This is again, I have a one-dimensional subspace. This is the data line, and now choose any vector. Now, this time around, I want to take a reflection of this vector about this line. Then, to do that, you draw the perpendicular line and draw another vector. And this guy, they must have the same length. Okay, so this is what I mean by reflection about the data line. I'm gonna call this transformation as H of data. Clearly, this is a linear transformation from plane to plane, R2 to R2. So this is H data of V. Reflection about now I am interested in finding the matrix representation of H data in terms of the standard basis. How to do that? how to find such a matrix representation? The first thing comes in my mind is just try to draw two standard vectors, standard unit vectors, and find their image under the H data, and then I can find the matrix representation of this transformation. But instead of doing that, I will try to take something more different approach. The idea is very simple. You know what I mean by the parallelogram, 평행사변형, right? So when you try to add two different vectors, then you have to apply the parallelogram law, okay? And the idea is V plus, now, what if I try to add these two vectors? My original vector V and my reflected vector H theta of V. If I add these two vectors, then the resulting vector must be this vector, starting from the origin and ending at this vertex. This vector must be V plus H theta of V, right? Okay. Now, this is again very interesting observation. If you take a look of the parallelogram spanned by the vector V and V theta of H theta of V, then this guy is not just a parallelogram, but this is precisely a diamond. Right? So this is diamond. Therefore, if you multiply 1/2 to this vector, then the resulting vector must be starting from here and ending at precisely the center of the diamond. Okay. Now what? So then this vector can be this vector from here to there has another name. What is that? This is P theta of V. This guy is actually precisely the same as the projection of this vector onto the data line. Okay. Okay. All right. So this equality is true for any choice of vector. This is true for all vector V in R2. Okay. Okay. From this equation, so from this equality, I want to solve this equality for H theta. Then maybe I can find a very nice matrix representation of this linear transformation. So let me try to solve this for H theta. So this is plus V is 2 times of the projection. Then this is H theta of V is 2 times projection minus V. So, and this is P theta minus identity, everything followed by vector V, right? And this final equality is true for any vector V. And therefore, the only possible explanation is this linear transformation is always the same as 2 times of projection minus the identity. Okay. So, okay. Now we almost got to the conclusion. Now, I want to find a matrix representation of the reflection in terms of the standard basis. Then this is precisely 2 times of the projection matrix minus identity transformation, the representation of the identity transformation in terms of the standard basis. Now, We already know this matrix. Okay, so which is nothing but this guy. Okay. Now, what do you think is this matrix? This is just a identity matrix. Okay. So 2 times of this guy and minus identity matrix. And this is 2 cosine squared minus 1 and 2 times sine cosine and 2 times sine cosine and 2 times sine squared minus 1. Okay. Then by using some trigonometric identities, this is the cosine 2 theta and sine 2 theta and sine 2 theta and minus cosine 2 theta. So this matrix is representing the reflection in terms of the standard basis. Okay. What happens if you apply 2 same reflections? Sorry, if you compose 2 same reflections, then it should be the identity, right? Reflect once, reflects twice, then means you reflected nothing. So therefore, has to be the identity. So again, so if you cannot trust this argument, then why don't you just try to multiply this matrix twice? Then you can easily be convinced that the result is precisely the identity matrix. You can prove things like this. And if you're paying attention to this first identity, then that means the inverse of the reflection is itself. Okay. The inverse is its own inverse. Sorry. Reflection is its own inverse. And the last one is, I guess this is the most interesting one. What happens if you compose not the same reflections, but if you compose, what happens if you compose 2 different reflections? Composition of 2 reflections is a rotation. Wait, is it really true? How do I explain this? Yeah, the remark number 1 and number 2, they were quite obvious to me, but number 3 is not that obvious. To explain, so I have 2 possibilities. I have 2 explanations. Oh, sorry. Yeah, so I really want to magnify this. So let me say this red line is the theta line. So therefore, this angle is the theta, and this blue line is the psi line. which are, so therefore the angle measured from here to there, it has to be psi. Now, I want to apply, so I want to reflect this guy by theta line first. Then this is H theta V. And I also want to reflect now this guy. I want to reflect this guy by psi line. Therefore, I get this, okay? Now, for simplicity, let me assume that the angle between the positive x-axis to this guy is the alpha. Then by keeping track of these angles, now you can easily be convinced that this final arrow, final vector, this guy has an angle measured from positive axis to this one is precisely 2 times psi minus theta plus alpha. Okay, so that means this one, if you apply h of theta and h of psi, then which is effectively the same as rotation about 2 times psi minus theta. This is my first explanation why composition of two reflection is the same as rotation. Well, but if you do not like this argument, then my second explanation is why don't you just try to multiply matrices of two reflections? Like so H psi so I want to show you that composition of two reflection is the rotation about 2 times psi minus theta, and which is equivalent to H psi STD and H theta STD is now multiplying this, so this is H theta. So if you multiply these two, then this is psi. So if you multiply these two matrices, then I don't want to spend so much time on computation. I will leave it as an exercise, but the resulting matrix is 2 times minus sine of 2 times and sine of 2 times psi minus theta and cosine of 2 times psi minus theta. This is what you get after multiplying these two matrices. But this final matrix is precisely rotation by 2 times psi minus theta. So the claim has been proved. Okay, so this is very useful thing to know. So if you reflect twice, then it's about basically rotation. Okay, so this is the end of the story. So, well, if the professor strength, so he gave us just these 3 examples about in this section, the rotation, projection, and reflection. So these 3. So once you understand these 3 examples, and once you know how to write down each of these matrices, the written in terms of the standard basis, then, well, basically you're done. But I just want to have a little digression on finding the same result. But I want to show you a completely different way, steps to find the exact two, just to derive the precisely same matrices, but different method. but I believe they are very important digression. And once my explanation is done, but I believe that you guys will understand, well, you guys will understand how to make reflections or rotations even in higher dimensions. The second trick that I will, from now on, I'm going to introduce the second trick, which will be namely a change of basis method. All right. So number one, I want to derive the projections of matrix. So I want to derive the matrix representation of the projection in terms of the standard basis. Oh, wait, we have already done this before. So the answer was this, right? But this time around, I'm going to use completely different method by choosing a different basis. This is the data line. So previously, when I was trying to get the matrix representation of this transformation, then I used the standard vectors, E1 and E2. But this time around, but there is, well, choice of standard basis vectors, they are only useful in psychological way. So we use the standard basis just because we feel very comfortable about this. But mathematically, the standard basis is, well, equally important than the other choice of basis. So in this case, I'm going to choose a different basis. This is my basis. Oh, sorry. I'm going to say this is my basis vector V1. And this is basis vector V2. For simplicity, I would say these two guys are unit vectors. Then what is V1? V1 is maybe cosine theta and sine theta. And for V2, this is V2 is obtained by taking the rotation of V1 by 90 degrees. So minus sine and cosine. Okay. So, well, I have chosen these two vectors. And are they linearly independent? Yeah, clearly they are linearly independent. So, and therefore, the V1 and V2, they form a basis of the entire space R2. Okay. So I'm going to give a name for this. V1, the collection of V1 and V2 is going to be basis of R2. Okay. Now we have chosen very special choice of basis vectors, but using this choice of basis vectors, now projection matrix is way easier than before. Why? Now I want to find a matrix representation of this projection matrix. So this projection, not in terms of standard basis vector, but in terms of the basis vector V1 and V2. To do that, I want to write down this resulting vector as a linear combination of V1 and V2. But what happens if you project the V1 onto the data line? It just carries over, doesn't change anything, which is the V1, right? I'm going to say 1 times V1 plus 0 times V2. Okay. Now, What about second basis vector? The projection of V2 under P theta is going to be nothing, zero vector, right? So 0 times V1 plus 0 times V2. Okay. Now, just looking at these two equations, we now know the matrix representation of P theta in terms of the basis B, in terms of the basis B. And I have 1 and 0 here. So 1, 0. And I have 2 zeros. Therefore, the second column has to be the 0 column. Okay. So this is a matrix representation of projection about my arbitrary choice of basis vectors V1 and V2. Okay, good. All right. So if I were a grader, and if that is your answer, then maybe I feel like I should give you the full credit for this. But however, this is not a mathematical statement. This is more like a political statement. So our convention is our final answer has to be almost always has to be written in terms of the standard basis. And so this is not that good. So basis or the choice of basis was not a standard basis. So therefore, from this guy, I will need to find a representation of the same linear transformation, but standard basis. How? Now, things are getting interesting. The change of basis. The change of basis trick is very useful. So especially whenever you have a matrix representation of some linear transformation in different bases, then using change of basis trick, then you can find the matrix representation of the same transformation but different bases. Just like this. My V1 is defined as cosine comma sine. So is cosine times E1 plus sine times E2. And likewise, V2 is minus sine E1 plus cosine of E2. Okay. This is great, but I'm going to put a extra redundancy. I want to consider as a identity transformation of vector V1 and identity transformation of vector V2. Okay, why is that? Because now let's go back to all the way to the beginning. So if you can write down any vector, any basis vector under some linear transformation, and the resulting vector was written in terms of this basis system, then this is your matrix representation. Okay. Therefore, this one can be understood as I have a matrix representation of the identity transformation whose input basis is B and output basis is standard basis. And this guy is cosine, sine, because we had the cosine and sine. And for the second column is minus sine and cosine. Okay. Agreed? All right. Now, let me try to imagine this. The same identity transformation, but this time the input base is standard and the output base is the B. Right. Precisely. So then this matrix is precisely the inverse of this matrix. Agreed? All right, we're almost done. Now, we try to find this. This is our final goal. I want you to find the matrix representation of the projection in terms of the standard basis. But I can think of this as a identity followed by projection followed by another identity. Okay. STD, STD, and this is identity STD B times B B. Oh, no, I messed up. Sorry. All right. So this is like reducing, exactly like the reducing fractions. This guy, they cancel out. This guy, they cancel out, and so you get this. Okay, so we are almost done. Hold on. So this is my basically. So in order to find the inverse matrix of 2 by 2 matrix, then you have to compute something. But in this case, this is an easy matrix. And I believe the inverse matrix is inverse of this guy is this, okay? So, yes. I will try my best not to mess up my computation. So this guy goes first. And this guy next. And this guy last. Okay. Now, all you need to do is just try to multiply, take a product of these three matrices. Yeah, this is a tedious computation. And I really recommend you to do this computation by yourself. If you do it, then you understand. But if you don't, then, well, maybe you can't. Then this is your answer. And which is precisely the same as this. Okay. Yeah, so we derive the same result, but this time by change of basis. And this trick is so universal, so you can actually apply this trick in many different places. Like reflection. Yeah, I have a data line. And I want to find a reflection, the matrix representation of the reflection in terms of the standard basis. But this time, I will begin from a different choice of basis. This is V1 and this is V1 and V2. And yeah, they are the same thing. Now, what happens if I reflect V1? It doesn't do anything. Just 1 times V1 and V2, okay? And H of V2 is this time 0 times V1, but -1 times V2, okay? So this choice of basis is very convenient. The computation of this matrix, is very easy. So therefore, H theta, the representation of this matrix, representation of this linear transformation in terms of basis B is just merely 1, 0, 0, -1. Yeah? Okay. Now, I want to find a matrix representation of the same transformation in terms of standard basis. Then which is this, okay? And which is this, okay? Then by tedious computation, it ends up with sine, cosine, to sine, cosine, no, 2 sine square minus 1. So this is your final result, which agrees to our previous discussion. Okay. All right. So the point is this: why? So just whenever you try to find a matrix representation of some certain linear transformation in terms of standard basis, just try. Well, if possible, then maybe you can try to find. You can directly find images of the standard basis vectors under that linear transformation. But if that is not possible, then maybe you can try to choose some clever choice of basis. Then matrix representation, finding the matrix representation in terms of that clever choice of basis might be much easier than before. Then once you find this matrix, then all you have to do is just multiply the change of basis vector on the left and on the right. Well, one original and the other one inverted. Then this is how you get the matrix representation of any linear transformation. Well, and I believe this is the right time to introduce the notion of the similarity transformation. Suppose that you have two matrices, and they are same, the square matrices with same dimensions. And also, suppose that you could find another matrix of same dimension, which is non-singular matrix M. Suppose that you found a matrix M such that A is M times B times A M inverse. If that is possible, then we say A and B are similar matrices. Or sometimes we say A is obtained by similarity transformation from B, or vice versa, whatever it is. So this is the notion of the similar matrix. Now, maybe at this point, by now, I am safe to say, if you have two similar matrices, then that implies those two matrices are representing the same linear transformation with different choice of bases. Okay. Similar matrices, they always represent the same linear transformation. Only the choice of bases are different because, well, but however, we cannot say one is better than the other one. They are all equally important because, well, there is no God-given choice of basis. Every choice of basis are equally important. Therefore, so therefore, similar matrices, they are the same thing. Maybe after the midterm examination, we will try to find how to find such a clever choice of basis. That is going to be our next big topic or issue after the midterm. But anyway, the idea is very simple. If two matrices are similar, then they are actually the same thing. Yeah, so therefore, even though this matrix and that matrix, those two guys, they are seemingly completely different, but essentially, they are precisely the same thing, right? Okay. Yeah. Yes. This exercise actually doesn't appear in our textbook. I just made it up. Sorry about this. I was really eager to bother you. But I really like this exercise. It's funny to say that. Yeah, I made this exercise by myself, and I really like it. So what do I mean by it? I don't know. So just forget it. I have a subspace. And this subspace S has been spanned by two vectors, 1, 0, 1, and 2, -1, and 0. Well, obviously, these two guys, they are linearly dependent to each other. So, and since S has been spanned by these two, therefore, this is a two-dimensional subspace contained in R3. Okay. Now, I want to define a linear transformation from R3 to R3. This is a linear transformation of reflection about S. So this is my picture. So I have R3, three-dimensional space, and I have some randomly chosen plane, two-dimensional plane. So yeah, since I have chosen these two choice of vectors, they are completely arbitrary. So I have a completely arbitrary two-dimensional plane here. And I want to find a matrix representation of this reflection. So you know what I mean by reflection. So if I have this vector and you reflect this vector about S, then you're going to get this. Okay. Then I want to find a matrix representation of this reflection in terms of the standard basis. Do you think you can do this by yourself? Okay, let us do this. Now, find matrix representation of this in terms of the standard basis. First, we give names for these vectors. 1, 0, 1, and 2, -1, 0, and now choice of breed. So I have chosen these two vectors. And for the last vector, so I am trying to choose the basis vector for R3. And I said V1 and V2 are the same as these two vectors. Now, for the choice of V3, I want my V3 to be perpendicular to V1 and V2 simultaneously. Do you think you can find such a vector, V3? Well, if you have attended the multivariable calculus course, then you know how to find a cross product of two three-dimensional vectors, right? So if you can compute the cross product of two vectors, then the resulting cross product of these two is going to be the simultaneously perpendicular to those two vectors. So I took a cross product of these two vectors, and so if you do not know how to do a cross product, then just try to find a orthogonal vector, another vector which orthogonal to V1 and V2. So it's not that is not horribly complicated. So this is V3, and clearly V1, V2, V3, they are linearly independent. So they are basis of R3. So V1, V2, V3 is basis of then RSV1 is what? 1 times V1, 0 times V2, and 0 times V3. Okay, because R1 has been V1 is already in subspace S, therefore cannot be reflected, so it remains the same. For V2 and V3, which is 0, 1, 0, but for V3, 0, 0, and -1. Okay, so representing this linear transformation in terms of this basis vector is 1, 1, and -1. Right? Right? Okay, now for the change of basis matrix, V1 is, well, identity of V1. So this is my V1. So 1 times E1 plus 0 times E2 plus 1 times E3. V2, V3 is 2, -1, and 0, and 1, 2, -1. So this is input basis B and output basis is STD, and the matrix is 1, 0, 1, 2, -1, 0, and 1, 2, -1. Okay. And inverse matrix is simply the inverse of this guy. Okay. Now our final goal is this guy represented by in terms of the standard basis, which is identity RS BB Oh, sorry. I messed up. My bad. Sorry. Okay. Because the canceling out always happens in this diagonal from the upper left to the lower right. So this guy cancel out, this guy cancel out. And yeah. So this is the answer. So you multiply this guy goes first, and this guy on the middle, and this guy goes to the last place. And you multiply these three matrices, then you get this answer. Suppose that you try to solve, well, you try to do this exercise by yourself. So suppose that you try to do this exercise without using the change of base tree. I believe then that should be way more complicated. The change of basis tree is very useful and universal, so you should be able to do this very fluently. And also, I will try to challenge you with another exercise. Just try to find a three-dimensional rotation matrix in terms of the standard basis. Then, in order to do that, you will need to have an axis of rotation. And for that axis of rotation, then suppose that you want to rotate everything about the theta radians in conventional right-hand rule. Then do you think you can find such a nice matrix? If your answer is yes, then maybe you're getting something from my lecture. All right. Thank you for your patience and see you next time.